Okay, so here we are again. This is, hopefully you guys can all see that. This is the MATLAB code for the implicit formulation. Again, we start off just entering the information. Here we discretize our domain. We discretize it into 11 nodes to start. And then entered in our implicit formulation. So you can see this expression here is our solution for one evaluation of the derivative. And we're evaluating that derivative at tj plus 1, right? And we've solved the entire expression to be explicit. So it looks a little different than what we had before. Okay, so this is, we're evaluating at tj plus 1, and then I just plot the two different solutions here. Let's see. Okay, so the red dots are our numerical solution, and the green line is the analytical. So you can see it's really stable. It doesn't oscillate or anything like that, but there is pretty significant error for the implicit method. We could try looking at maybe 101 nodes, see how that does. Okay, so for 101, now it's pretty accurate. But you do see it, yeah, it's not perfect, right? At the very end, it's starting to diverge a little bit. Okay, so that's implicit. Now for Crank-Nicholson, same deal, but we've now got two evaluations. So we have our derivative evaluation with the current time and the current temperature, and the one at the end of the time step, and this has been solved explicitly. So I guess I can't really wrap it. Anyways, you'd have to see how it's actually solved out, but it should match our equation that we have, this one here. Right, this is our solution. So we just implement that here, but it's only j plus 1 only appears on the left-hand side. Okay. Unless you have time, which time is defined beforehand, so you're okay there. Okay, so anyway, let's evaluate this for 11 nodes. For 11 nodes, you can see not only is it stable, but it's remarkably accurate. Right? So you could pretty much get away with this solution if you wanted to. Actually, if you're curious, it remains very stable down to even small numbers of nodes. Right? So even with 5 nodes, you're still pretty accurate, which is kind of crazy for, right, we have this weird function and it's changing pretty rapidly, and it's still doing a pretty good job predicting it. So, okay. Any questions on those methods? Yeah. So as you increase the order, I guess inherently it becomes more stable because you're more accurate, I guess. But the thing that really increases stability is the implicit part of the implicitness of the equation, where you're looking at something, you're evaluating the derivative at different times and then taking the average of that. That's really what increases stability. So, yeah. But for a second order compared to first order, it would be for the same number of nodes, the second order is going to be more stable. Okay. So then the other things, the other last couple of methods we're going to talk about for numerical here are integral methods. Okay, so just kind of written the notes out here, but an integral method is a method where you are providing to some software package, let's say it's EES or Matlab, you're providing to that a way of evaluating the state equation. You just give it a function. Okay, so you're calculating the state equation. You go through and derive that state equation. But ultimately, what you're doing is you're providing that state equation to a function or to a capability that the software has, and then the software will manage stepping through time, keeping track of the sort of progress of evaluation. Okay, so there's, I guess, 2 ways I want to talk about to do this. One is in EES and one is in MATLAB. So in EES, the way to do this is, let's say we want to evaluate some function f or some variable f, right? We have an initial value of f, and then if we're going to evaluate how that entire function changes over time, we can do that by taking the initial value plus the integral of what has sort of happened from the beginning of time to the end of time. As long as what we're integrating is our rate equation, our state equation, right? Our rate of change. So we're evaluating our derivative, add that to the original value there, or the initial value, and that gives us a value at any particular time. Right. So what I'm saying is, if you have, if you know the initial time to be, say, t equals 0, and you integrate from 0 to the end of the time that you want to look at, what you're predicting with that integral plus the initial value is going to give you the temperature at the end of time, at T-sem. Okay. So that kind of confusingly, but does that sort of make sense to everybody? Okay. So maybe this is better just to look at an example. So what we can do here is, let's actually open, do I have EES open here? I think it was this one, lumped integral. All right, so in EES you can come in and provide this integral function, or provide your state equation and then put it into the integral function. So we'll do that. Options. Okay, so here's the same problem that we have, right? We're looking at the same thing. And then what we're doing down here is we're providing an estimate dt dt. This is like at a single integration variable of our state equation, right? This is our state equation that we came up with before. So right, notice that I'm not writing everything out kind of the same way, where you have like tj equals, or j plus 1 equals tj plus stuff. Now all we need to do is get to having the state equation. That's kind of the convenience of these methods. So you get the state equation dt dt, which is what we said it was here. T infinity is indexed, or is a function of time. So you have a function for that up here. And then all you have to do is pass this thing to the integral function. So what the integral function is doing is it's taking your integrand here. It's going to integrate it from over some variable time from 0 to T-sem, the thing, the thing you're specifying. So if I do this, let me just comment out this row first. If I solve this, hopefully it works. You can see it's doing something kind of different. It's doing an integration, right? And I can look at the results, and I should see my temperature is, okay, 373. So which temperature is that? Right? At what time is that temperature? Yes, right? Because you're reporting T after kind of adding that full integral to your initial condition. So that's T-sem. So what if I wanted to see all the values in between, right? In between 0 and T-sem. Well, it turns out there's a way to do that in EES. It's not entirely obvious, but there's something called an integral table directive. So you come in here, add this thing called integral table, $sign integral table. And then what you want to give it is the thing you're integrating with respect to, which is time. And that should match what's up here. And then a list of anything that you want to report along with what's being integrated. So we want to see temperature T. It may be that we'd also wanted to see, I think it's comma separated T infinity. If we had an array of that, for example, in this case, we just have it as a function, so we can't do that, but you could list off the things that you want to include. And then when you solve this, let's see, solve it again, continue, and you go to Windows, there's something called integral tables. Okay, and the integral table is going to have now every single time that it evaluated this integral and the corresponding temperature. Right? And if you scroll down, you can see it's actually automatically doing quite a few steps on this. Right? You can see how it kind of plays out. So then you can come in and say, I want to plot this. I'm going to do, integral tables. I'm going to plot temperature as a function of time. And there's our solution. Right? Yeah. Like it's a numerical integral. Yeah. So it's evaluating the integral numerically, I believe. Yeah. Yeah.
So are they using the same method, so like the numerical method that we're
I actually don't know exactly how it's evaluated, but when you so when you put everything in ease into like a matrix format, you know, everything that appears in that matrix is a coefficient. So having a coefficient on a variable is like taking the derivative of that variable. Right? So you have access to basically the derivatives of the functions by the way this solver is set up. Right? So when you're doing the integral, you kind of have right there a lot of information. I don't know exactly how they go about whether it's yeah, I maybe should learn a little bit more about that, but yeah. So you didn't miss it. I was going to talk about that next. So if you look at, if you want to set the number of steps, there's a couple ways to do that. The easiest is to go to options, preferences. The same place where you set font size. But there's this tab called integration here. So integration has a bunch of options. You can set the step size. You can set limits on evaluations and all that. So that's one way to do it. There's actually another way to do it that involves a directive, and it's this one up here. So at the very top, you can say integral auto step, and then you can provide all these different arguments. And this is what's specifying how the integration actually occurs. So the way that these integral methods work, unless you really constrict it, is it'll automatically compute the local error associated with the evaluation. And then it adjusts its step size to get to below whatever threshold you say here. So if you look at the actual time step size here, the time step size is changing. Right? It's not a constant increment. And that's the power of these methods, is it automatically will. It starts off with a constant value, so it's stepping at 1e⁴, but by the time it starts seeing a rate of change, it'll shorten up the steps if it needs to. Yeah. So it's a really powerful method. You just have to get the state equation. That's kind of your job.